This is the V-22 Osprey. It takes off like a helicopter and cruises at 280 knots, faster than any helicopter ever built. But during the transition between those two modes, it cannot autorotate like a helicopter or glide like an airplane. There is no good option if something goes wrong in that window. A helicopter with a failed engine can autorotate to a survivable landing. A fixed-wing aircraft can glide. The Osprey, in conversion, can do neither. The V-22 solves a problem no prior aircraft had to solve. Conventional helicopters and fixed-wing aircraft occupy separate aerodynamic regimes and stay there for every flight. The Osprey moves between them twice per sortie, once on departure, once on approach. It takes off in helicopter mode with its nacelles pointed straight up, transitions to airplane mode for the cruise leg, then converts back to helicopter mode to land. The capability is genuinely useful. The transition is genuinely dangerous. Understanding why requires understanding what happens to lift during those 12 seconds when the aircraft is neither thing. The nacelles sit at each wingtip and house the engines and proprotors. In helicopter mode at 0 degrees, the proprotors face skyward and generate vertical thrust. The aircraft rises like a conventional rotorcraft. At 97 degrees, the nacelles have rotated forward and the proprotors face the direction of flight, generating horizontal thrust while the wing generates lift. The extra 7 degrees past true vertical ensures proprotor wash clears the wing surface during hover. Without that margin, downwash striking the wing reduces hover efficiency enough to cut payload capacity on every mission that requires it. Between 0 and 97 degrees, rotor lift is declining and wing lift has not yet fully replaced it. That window is 12 seconds long. It is the most aerodynamically marginal phase of every flight, and every sortie passes through it twice. The proprotors span 38 feet each, roughly the length of a school bus, making them larger than the main rotor on most military helicopters. That size is not a design preference. At the Osprey's combat weight of approximately 47,000 pounds, the combined weight of 4 fully loaded pickup trucks, smaller rotors cannot generate sufficient hover thrust. The diameter that solves the hover problem creates a separate problem on descent, one the program spent a decade learning to bound. For now, the nacelles are rotating, and 47,000 pounds of aircraft is moving between two aerodynamic states simultaneously with nothing to fall back on if the process stops halfway. The gearboxes shift pitch. The proprotor disc tilts forward as the nacelle rotates. Inside the cockpit, airspeed builds on the display. 80 knots, then 120, then 160. The rotor wash that was driving straight down is now driving straight back. The cabin noise changes pitch. The vibration frequency drops as rotor RPM stabilizes in airplane mode. The wing is flying. 12 seconds. The aircraft is now a turboprop. But the nacelles rotating is only what makes the aircraft work. The cross shaft is what keeps it alive. Both proprotors are mechanically connected by a single drive shaft running through the wing. It is approximately the diameter of a man's forearm and spans the aircraft's full 84-foot width. If one engine fails in any flight phase, the surviving engine drives both proprotors through this shaft. The dead side keeps turning. Asymmetric thrust, one proprotor producing full power and the other producing nothing, would roll an aircraft this size faster than any control input could counter. Without the cross shaft, a single engine failure during conversion is unrecoverable in the time available. Too rigid a shaft and thermal expansion at operating temperatures causes binding at the gearbox interfaces, introducing load spikes that propagate through the wing structure with every power change. Too flexible and torsional oscillation at high power settings transmits destructive vibration through the same structure. The shaft operates at a torsional stiffness calculated to avoid both failure modes simultaneously. It functions in Arctic cold and desert heat alike. It just has to work. And the biggest threat to that aircraft is not mechanical. It is aerodynamic, and it only exists in one specific phase of flight. But the nacelles rotating is the easy part. What happens to the air around those proprotors during a descending conversion is what the program spent years learning to manage, and several aircraft learning to survive. Vortex ring state is not unique to the Osprey. Every helicopter can enter it. It occurs when a rotor descends into its own downwash, the air the rotor just pushed downward, at a rate fast enough that the downwash cannot clear the rotor disc. The inflow and the downwash collide at the rotor plane, creating a recirculating vortex that chokes lift progressively. The rotor is working hard and producing almost nothing. In a conventional helicopter, recovery requires applying forward cyclic to fly the rotor disc into clean air. That requires airspeed and altitude the aircraft may not have. In the Osprey, the problem is compounded by proprotor diameter. At 38 feet per disc, each rotor generates a downwash column wider than most military helicopters produce. The aircraft descends into a larger, deeper disturbed air mass. Onset occurs faster. The recovery window is smaller. Below a certain altitude at combat weight, recovery is not available at all. The rate of descent indicator climbs past the caution limit on the display. The warning tone arrives before the pilot consciously processes the number. Roughly 800 feet per minute is about the speed of a descending express elevator in a tall building. The nacelles push back toward vertical to recover rotor thrust. The aircraft shudders as the proprotors re-enter undisturbed air. The correction cost altitude. Low over a landing zone in a tactical approach, altitude is exactly what is not available. The descent rate was wrong by 100 feet per minute. On a training flight, that is a caution and a correction. On a night approach to a contested landing zone at combat weight, it is the beginning of an unrecoverable sequence. The solution was not to change the rotor. It was to change what the crew is allowed to do with it. The conversion corridor defines the altitude and airspeed band within which the nacelles may transition from airplane mode to helicopter mode during a descent. Below a defined altitude floor, roughly the height of a 12-story building above the ground, that conversion is restricted. The crew must arrive in helicopter mode before descending through it. This means the conversion happens higher up, at higher airspeed, in cleaner air, with more recovery margin. What it costs is tactical flexibility. A steep diving approach, the kind that reduces exposure time over a defended landing zone, requires conversion at low altitude, close to the ground, at a descent rate that pushes toward the vortex ring boundary. The restriction prevents that profile. The landing zone may be accessible. The approach geometry may not be. The crew plans the entire ingress around that constraint before the aircraft leaves the ground. The most automated military rotorcraft in the Marine Corps inventory still requires the crew to set every condition the automation depends on. The crew controls nacelle conversion rate. The flight control computers enforce the schedule, command too fast to transition, and the computers override. But the decision of when to begin conversion, at what altitude, at what airspeed, under what weight and wind conditions, belongs entirely to the crew. The computers execute. They do not assess whether the conditions are acceptable. Too early an initiation and the aircraft enters the transition window with airspeed that cannot be bled off before nacelles reach vertical. Too late and the aircraft arrives over the landing zone still partially converted, with nacelles at an angle that provides neither efficient rotor lift nor wing lift, at an altitude where neither condition is recoverable. The nacelles are already rotating back toward vertical. The nacelles begin rotating back toward vertical. The aircraft that was cruising at 280 knots is becoming a helicopter again, at low altitude at night, over a landing zone that may be 50 feet across. Before any of that happens on ship deployments, the aircraft has to fit. The V-22 has an 84-foot wingspan in cruise configuration, too wide for most ship elevators and incompatible with carrier deck spacing. The blade fold system handles this. Each proprotor has 3 blades. In the fold sequence, all 6 blades on each rotor hinge inward, sweeping back along the nacelle. The nacelles then rotate to a stow position, compressing the entire assembly against the fuselage. The full sequence takes approximately 90 seconds, roughly the time it takes to walk a city block at a deliberate pace. A blade that fails to lock in the folded position grounds the aircraft until the mechanism is fully inspected. A blade fold that activates during flight due to a system fault produces structural failure of the rotor head. There is no recovery procedure for the second outcome. Every blade lock indicator reads green before the aircraft moves toward the elevator. The combat radius in airplane mode runs approximately 700 miles unrefueled, roughly the straight-line distance from the East Coast to Chicago. In helicopter mode at combat weight, fuel burn increases substantially. The mission profile is designed to minimize time in helicopter mode, fly the transit as a turboprop, convert close to the objective, execute the approach and landing, and leave. Every extra minute in helicopter mode at combat weight reduces the return leg margin. The aircraft was not designed to loiter over a contested area in helicopter mode. It was designed to arrive, deliver, and leave before anyone adjusts to its presence. The descent back into helicopter mode is the most constrained direction of the entire flight profile. Going from helicopter to airplane on a failed engine is survivable. The cross-shaft keeps both proprotors turning, and the wing generates lift as airspeed builds. Going from airplane to helicopter at low altitude with a full combat load tightens every margin simultaneously. The aircraft must decelerate through the conversion corridor while descending. Too fast and the aircraft arrives over the landing zone with airspeed it cannot bleed off without climbing, defeating the entire tactical approach. Too slow and the descent rate climbs toward the vortex ring threshold before the nacelles complete their rotation to vertical. The nacelles reach vertical. The descent rate drops. Below the aircraft, the combined downwash from two 38-foot proprotors produces surface winds roughly equivalent to a Category 1 hurricane, spread across an area the size of 4 basketball courts directly beneath the hover point. Personnel approach along vectors pre-briefed relative to the aircraft heading, clear of the downwash column. Anything unsecured on the landing zone is already moving before the aircraft reaches 50 feet. The Osprey touches down on its main gear with the proprotors still generating partial lift. The load the landing gear actually transmits to the ground at touchdown is lower than the aircraft's gross weight because the rotors have not fully spooled back. This changes the braking distance, the ground roll, and the bearing strength the landing zone surface must provide. The weight on wheels figure the aircraft imposes is not the number most landing zone planners use. Engineers with the correct data know the difference. The distinction matters when the landing zone is soft ground or a ship deck near its weight limit. The proprotors spool back, the nacelles hold vertical, the ramp drops. The troops were in the air 40 minutes ago, 700 miles away.